Hey guys, welcome back. In this video, we're going to think carefully about one idea, directional derivatives. By the end, I hope this idea feels simpler and more connected. Imagine you're standing on a hill. You can walk in any direction. Some directions go uphill, some downhill, and some feel flat. The directional derivatives tells us exactly how steep the surface is in whatever direction we choose. So today, we're not just asking about how a function changes, but we are asking how it changes in a specific direction. Sounds pretty interesting, right? Briefly, uh, let function f of xy be a multivariable function. It's a multivariable function. Um, I'm not going to tell you about the gradient that deeply, but to talk about directional derivative, it is essential to know just briefly what gradients are. So the gradient of the function f of x and y is the vector valued function. It's a VVF, such that gradient of f is partial x of xy and partial y of xy. So this is the gradient. We use this del operator. It's like a upside down of the delta sign. So this is gradient. And the gradient is a vector. It's just a vector. And each component is partial derivatives. Um, Remember, partial derivatives are just the slope along x or y axis. But in real life, we never move exactly along x or y direction, right? We move in an arbitrary direction. That's why we need directional derivatives. A directional derivative measures how fast a function changes when we move from a point in a specific direction. To talk about direction only, not speed, we use a unit vector. So remember, unit vector always tells us the direction, but without speed. So in other words, the magnitude of the unit vector is always one. So using that property, uh, let's say if the unit vector, let's say u, is equal to u1, u2 is a unit vector, then the directional derivative, the directional um, derivative in the direction of the unit vector u is, we write this capital D sub u of f of xy. And this is equal to gradient dot product with the unit vector. This is the directional derivative. It's the formula. Um, as you know, we can rewrite this function in expanded form. Uh, Let me write it here. And that's just equal to partial x times u1 plus partial y times u2. And also, we still can rewrite this equation by the definition of the dot product. This is just equal to the magnitude of gradient times the magnitude of the unit vector times cosine of the angle between two vectors. Um, do you see where we are heading to right now? So it looks already interesting, right? So the unit vector, the magnitude of the unit vector is always 1. So we don't have to write it. So we can simply just say the directional derivative is just equal to the magnitude of the gradient times times cosine. So it is simply the dot product between gradient and the direction vector. Um, Remember, dot product always gives us a number. The output is a scalar value. And the number tells us the slope of the surface if we walk in that direction. So the output, the number the directional derivatives gives us, has the meaning. So if the number is positive output, that means the function increases. Remember, when derivative gives us positive value, then the function increases, right? It's the it's the same sense, same mechanism. So if the directional derivatives has the positive value, then it means the function increases. In other words, you are walking uphill. If it is negative, so let's say this is uphill. Um, if it is negative, it's the opposite. You are walking downhill because the function decreases. So downhill. And when it is 0, this is where the thing gets more interesting. Um, 0 means the surface in that direction at that point is locally flat. So you're moving along a level curve. So it's a locally flat. The reason why is that because the dot product depends on the cosine of the angle between two vectors. And although I'm going to tell you more deeply about the gradient in the next video, but the thing is, gradient always points in the direction of the greatest increase of the function. So the direction where gradients points is the uh, maximized slope. So remember, when the dot product gives us 0 value, that means um, the angle between two vectors is perpendicular, right? So one is gradient, one is unit vector, the direction we choose. The gradient points in the maximized direction, and the direction we choose points perpendicular. That means um, the gradient points in the maximized direction, while the direction we choose points in the minimized direction, which is 0. So that's why when the directional derivative gives us 0 value, we are walking on a locally flat surface. Um, Pretty interesting. Yeah, so we can say that the magnitude of the gradient gives the maximum value of the directional derivatives. So directional derivatives let us ask more flexible question, not just how a function changes, but how it changes in any direction we choose. And once we understand directional derivatives, the gradient becomes much more meaningful. It's simply the direction of fast this change. Um, all right, that's it for today's video. So simply directional derivatives let us find how steep the slope is in whatever direction we choose. And it's fundamentally, it's just the combination of dot product and what it's called gradient. And gradient, because gradient always points to the steepest hill, and we use the dot product with the direction vector. So it allows us to figure out um, how steep uh, how steep the direction we choose compared to the gradient, which is maximized steepness. I hope you uh, I hope you feel more better, more simply connected. And in the next video, I'm going to talk about more deeply about gradients, like why, the reason why gradient always points in the maximized slope at any point we choose. Um, that's the proof is pretty interesting. It's briefly derived from multivariable chain rule and also directional derivative. So please be excited, and until then, let's keep things simply connected. I will see you next time. Thank you.